Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss about working proportions and design of Pelton wheel. While designing the Pelton turbine or Pelton wheel and while solving the problem of Pelton turbine, we need to keep in mind some terminologies and we need to remember some formulas also while calculating or while designing the Pelton turbine. So first of all, I'll tell you that first one is the velocity of jet at the inlet condition. First terminology I can consider this is the velocity of jet at the inlet condition. The velocity of jet at inlet. So this is actually, we know that this is V, velocity V is to indicate by capital V. So at the inlet condition means we need to consider this is V1. So this V1 is to calculate by the formula of CV root over of 2GH. Actually, to understand this concept, like this is the formula, and this formula was derived from the conservation of energy principle. Okay, this formula actually calculated or derived during the conservations of energy principles. So actually here we have the runner part is there, and in this runner we have that number of blades are fixed in this. So here you can see these are the blades are there which is fixed on the or which is mounted on the runner. Okay, these are the number of blades which are fixed. Now here nozzle is there and the water is striking on this blade, on the center of this blade, and this is the nozzle and the pipe is connected. Actually this is the pipe, or we used to call it a penstock. So here we have the dam portion is there, like the water storage portion is there here, and you can say this is the storage of water, and from here we need to, the water need to supply to this one. So at this bottom of this we have the tail race, and this is bucket, this is called bucket or vane, or we can say blade also. Okay, and the middle of the part is connected with the shaft, and the shaft is connected to the generator here. So this is connected to the generator box, so that from there the electricity is to produce. And as I told you, this is runner, and this is, as I told you, shaft. Anyway, so this velocity of the jet which is striking this blade, that is called here velocity of jet at inlet condition, that is V1. So we can calculate by this formula. And here CV equal to the coefficient of velocity. Here CV equal to, this is coefficient of velocity. Okay, and the value is to mostly near about 1 only. So like 0.98 or 9 is to consider for here. And H we can say this is the net head of the turbine. This is the net head on turbine. So what is the meaning of net head? So as I told you, this is the tail race, this portion after striking here the water is to fall here. So this part is called tail race. Okay, so the distance from this tail race zone to this upper level, like up to what level the water is present here, so this distance is called actually the gross head, that we have discussed previous lecture. And when it is in rest condition, okay, this distance from here to here, and when the water started moving through this penstock, and striking this blade at the turbine, so obviously there is some losses will be there during this flow. So that if you remove the losses, that is HF, so remaining this thing is called the net head, or that is H, that is the thing net head on the turbine. So these losses used to minus the pins. If you want to calculate the net head, so we can calculate by Hg minus Hf, and Hf will be Hf can be calculated by the formula of Darcy-Weber's formula, that is HFL V square by 2dg. Anyway, so these are the terminologies are there. And here g, this is acceleration due to the gravity, that we know the formula, that we know the value of 9.81. So this is one terminology to find out the velocity of jet for one. Now the next one is, second one is the velocity of wheel. The velocity of wheel. So the velocity of wheel can be calculated, but we have two options out there. One is u equal to, we can write the same thing like phi into root over of 2gh. Phi into root over of 2gh. Here phi equal to what? Now phi equal to, this is speed ratio. This is called speed ratio, and the value of the speed ratio is to vary from 0.43 to 0.48. And the speed ratio actually used to define, or used to call it a velocity ratio also, or this is also called as velocity ratio. So this velocity ratio actually how to define, like the tangential velocity of the vane with respect to the velocity of the water jet, we can calculate. And the velocity of wheel also can be calculated. If you want to calculate the velocity of wheel, this one, this is the wheel is there, this is the wheel is there, okay, that also can be calculated. So one more thing, the plate, like what is the velocity of plate is suppose given, that also we can calculate by this formula like u, or here you can write u, u1, u2, okay, all these things will be taken by this pi dn by 60. This can be calculated by pi dn by 60. So d is the diameter. Okay, this is one formula, this is another one. Anyway, we can use any one to calculate this, based on the data given. Now the angle of deflection, second one is the angle of deflection. So angle of deflection, actually when you draw this velocity diagram for the bucket, there you can see the angle of deflection of the jet through the buckets, or that is to consider actually 165 degree. Okay, 165 degree if the angle is not given. If the angle is given in the question, then no issue. If it is not given, then directly you can consider the value of angle of deflection is 165. So you may have confusion, what is this angle of deflection? Actually this is the bucket is there, suppose, and here at this center of this point the water is striking here. So at this point actually the runner the splitter part is there. So and if you see, this is the blade is there, this is the bucket or blade, and the angle of deflection means the angle of this jet with respect to this blade, what angle. So this is called angle of deflection of the bucket, of the jet, you can say, because jet is coming out from here at this velocity. So this is called angle of deflection, that is 165 degree. If it is angle is not given in the question, then we can consider this one. Okay, and the next one is, the fourth one is, you can calculate the mean diameter. So mean diameter, or used to called, this is pitch diameter also. Mean diameter or pitch diameter, that is d. That is d. So this one actually already I have written this formula. So from here we can calculate the value of d. From the formula of this velocity we can calculate. So you can write this is 60 into u by pi into n. So here n equal to, we know the speed of the runner, that is n equal to speed of the runner. Okay, and the next one is jet ratio. The next one is jet ratio. So jet ratio actually it is having the definition is like it is defined as the ratio of pitch diameter. So it is, okay, let me write the formula for this. Actually jet ratio is to indicate by m. Okay, it is to denote by the ratio of like it is the indication of m, and it is the ratio of like the ratio of pitch diameter d of the Pelton turbine to the diameter of the jet, to the diameter of the jet. So diameter of the jet is, you can write, this is, okay, here I can write d equal to pitch diameter or mean diameter, pitch diameter, and here d equal to, I can write this is diameter of jet. This is diameter of jet. So the ratio, jet ratio is nothing but m equal to d by capital D by small t. and mostly the jet ratio is to 12. For maximum cases, most of the cases is used to consider 12. Okay, the next one is number of buckets. The next one is number of buckets. So how to calculate how many number of buckets should be on the wheel? So on the wheel, or we can say on number of buckets on the runner. Runner, rotor, wheel, all are same wordings, same meanings. So this can be calculated. That is, suppose the indication is Z. So this could be calculated like 15 plus d by capital B d by 2 into small d. So this one we can write, this is 15 plus 0.5 m, because m equal to d by d. D by d and 1 by 2 is nothing but 0.5 m. Okay, this is about the number of buckets on the runner. The next one is number of jets. Number of jets. So the number of jet is nothing but this can be calculated the total rate of the flow. The total rate of the flow through the turbine. Okay, by the rate of flow of water with a single jet, through a single jet. Then we can calculate the number of jets. Okay, this number of jets is nothing but, to calculate this one, we need to consider the total rate of flow through the turbine. The total rate of flow through the turbine by the rate of flow of water through a single jet. Then we can identify the number of jets. So these are the terminologies are required for working proportions, or we can say to calculate the Pelton wheel design, or to identify the designs, or to calculate the velocity of each and individual parameters. We need these are the terminologies. The next one, this is about the working proportions. The next thing is design of Pelton turbine. So for the design of Pelton turbine, yeah, let me give another one. So yeah, for design of Pelton wheel or Pelton turbine, which means we need to calculate, or we need to identify, we need to determine some terminologies are there. Okay, what are the terminologies to design the Pelton wheel? The first one, we can say we need to identify what is the diameter of jet. What is the diameter of the jet? If the values are given, there is no issue. If it is not given, then to design this Pelton turbine, then we need require these values. These terminologies or these values are required to design the Pelton turbine. First one is design of jet, which I told you, that is small d. Similarly, the next one is diameter of wheel. Diameter of wheel. So diameter of wheel, this also we used to mark is capital D. Actually, here mean diameter was taken capital D, or here you can consider diameter of wheel can be taken D star also. Okay, if same values, same diameter, if you don't want to keep it, then you can keep the D star or D. Or this D also used to call the same diameter, because mean diameter of piece diameter is nothing but we can consider also diameter of the wheel. Okay. The next one is width. The next one is we need to calculate the width of the bucket. So what is suppose the bucket, in the sense, see, the bucket structure will be like an if you see, yeah, so this is the splitter. And yeah, at the splitter, the jet used to strike on this, so that the water used to come out from this point. Okay, so the width, as I told you, the width of the bucket. So what is the width of the bucket should be, or how to calculate? So we need to know that width of bucket need to be identified. So this actually generally the width of the bucket we used to calculate by 5 into D, 5 times diameter of the jet. The next one is depth of the bucket. What should be the depth of bucket? So depth of bucket is to calculate, this is 1.2 into diameter of the jet. Now see, this is our width, and what about the depth? So how much depth is there of the bucket? If I draw a line, then what is the depth of this bucket and how to calculate it? So that will be calculated by this 1.2 into D. Yeah, next is we need to calculate, or we need to identify number of buckets on the wheel. Number of buckets on the wheel, this one. So this one already I told you how to calculate. So this is another one, the number of buckets on the runner. So these are the some terminologies are required, or these are the working proportions of Pelton wheel, or to design a Pelton wheel we need these are the datas. So I hope you understand this lecture. This is a simple one, only you need to remember these formulas. I hope you understand. Still, if you are having any doubt regarding this, you can give a comment in the comment box. Thank you all.